Okay, so we'll start today with filter circuits. Now, in the earlier lecture, we have seen that for a conversion of AC signal to DC signal, one of the elements or one of the components is power transformer. It can be a step-down transformer, center tap, or you can have center tap step-down transformer. Then we have studied three types of rectifier circuits: half wave, full wave center tap, and full wave bridge rectifier. Now, there is another process called as filtration. Now, what this filtration process will do? It will do exactly as follows over here. It will filter out the AC component as less as possible. So right now AC component is this much over here, right? See, this is the amount of AC which is present, right? Now here if you can see the AC component has reduced quite a lot and it's moving towards the DC component, right? The next action from this to this is a regulator. Okay. Before that we will have a filter circuit. So right now we will see how a circuit will transform a rectified output to this filtered output and how it happens. Okay, so y'all in a syllabus have only one type of filter. We'll study only one type. There are actually many types. We'll study only capacitive filter. So let me introduce you the filter concept. This is from a different subject. Output of rectifier. Just listen carefully. This is just for your information. They're not going to be asked this in your exam, but this is for your knowledge. The output of the rectifier is pulsating in nature. What it means? It means it contains AC plus DC. I hope it is visible to you, whatever I'm doing over there. Okay. So what do you mean is, if you expand that equation, you will have a DC component and a AC component. So this is that DC component which we have 2 Vm by pi. We find out now we have average for full wave rectifier. It is 2 Vm by pi, right? And this is my AC component. In order to reduce or remove this AC component, we apply the filter circuits. All right. Have you heard of Taylor series? So this is the Taylor series expansion. So higher order terms we neglect, but this is the AC component which we have to reduce it. Why we want to reduce it? Because we want DC out of AC. All right. And in order to remove AC component, we use filter circuits. To filter, what it will do, it will remove the AC or reduce the AC component from the AC plus DC signal. There is a pulsating DC signal. So that's the job of a filter, or it will smoothen out the DC. So what I mean is, if you have this kind of a waveform, okay, what is this waveform? I mean, whose output is this? No, what is this output of? It's output of full wave rectifier. Whether center tap or this it will do. What does the filter circuit will do? It will smoothen down this waveform. So this has over here, it will discharge like this. So if you see this waveform, it will be looking like this. Okay. So this is what the filter circuit will do. It will smoothen out your signal, pulsating DC signal, which will be closer to your AC. Now this is closer to DC or this is closer to DC. So definitely this one, right? So that's why we study filter circuits. See, this is what it will do. Generally, what is the reactance offered by the inductor? XL, 2 pi FL. And at frequency equal to 0, the reactance is 0. And at infinite frequency, this is infinite. So it means inductor acts as a short circuit for DC component. It passes DC whereas it blocks AC component, very important property of inductor. Whereas another property of inductor is it opposes any sudden change in the sudden change in current. Okay, so that means your transformer is consisting of inductive coil, right? So it doesn't support DC, it only supports AC component. Whenever you apply AC signal to an inductor, then inductor opposes it. Okay. Yeah, the reactance offered by the capacitance is Xc, which is 1 upon 2 pi Fc. That means for frequency 0, impedance is capacitive reactance is infinite, and for frequencies very high, it is 0. This means capacitor acts as open circuit for DC component. That means it blocks DC and allow AC to pass through. All right, I mean making it clear. So therefore, you always connect capacitor in parallel with the load because you want to block DC and allow AC to pass through. Okay. So with this, we have four types of filter circuits: inductive filter, capacitive filter, inductive capacitive filter, and pi filter. Okay, you all have. We will teach only one capacitive filter, but you should know there are different types of filter circuits: inductive, capacitive, LC, and pi filter, or CLC we can say. Okay, so this is my L filter. L filter is always connected in series with the load. Capacitor filter, I told you why it is connected in parallel. Why it is connected in parallel? Because it allows AC and blocks DC. Okay, so we are not interested in the different other filter circuits. We will start with the capacitive filter circuit only. Okay, so write down over here. This is lecture number 35. All right. So we will consider full wave center tap rectifier with a filter circuit. So write down capacitor filter, or it is also called as C filter. I don't know whether the recording will be fine or no, because I require a charger. With a charger, the recording comes very good. But it's okay, fine, no problem. So let's draw this capacitor filter, and which rectifier we will use over here? Full wave center tap rectifier plus filter circuit. So how does it look like? So let me draw that circuit with over here. So I require a center tap transformer. Here is my AC mains. So please dwell on with me. This is my AC mains. Then we have a laminated core. And then we have a center tapping. Okay. So here we have one diode over here and another diode over here. Alright. And if you see carefully, this is connected together. And this is connected to the ground, right? So what if normally we connect it like this, right? This is connected to ground. Normally we connect it like this, correct? Yes or no? But what if we connect the center tapping from here to here directly? It means the same, right? So this is also ground to this center tapping. Instead of connecting it to the ground, just wait. We'll directly connect it over here, and that will serve as a ground. Yeah. Okay. So let me draw this again. So this will act as the ground now. So I have this resistor over here, and also have this capacitor. I'll connect this capacitor over here. So this is C, this is R, L, and here is my output, plus minus V out, and this is my ground. So it's the same circuit only. This is ground. So what you will have over here? Here you will have this kind of a signal, right? And here you will have out of phase signal. Yes or no? That means here you will have Vm sin omega t, here also Vm sin omega t. We know how this circuit works, right? But we will have one important element in terms of this capacitor. Completed? Okay. Completed the diagram. This is my circuit diagram for a capacitive filter. Now we have to draw the waveforms and also explain. Now, before doing that, let me just revise. During the positive half cycle, what happens? Just write it down, two sequence over here. During the positive half cycle, which diode is on? Which diode is on during the positive half cycle? D1 is on. Okay. And D2 is off. And during the negative half cycle, D2 is on. This is clear, right? So basically, if I draw the waveform over here, let me draw it. I am drawing it a little bigger. I'll tell you the reason why. Don't draw it right now. You will draw it later on because there will be a lot of changes. I'm drawing it a little big for a reason. So can you see this three full wave rectified waveform? Is it true? Yeah. So from 0 to pi, from pi to 2 pi, and from 2 pi to 3 pi, you get this rectified output. So this dotted line which I show over here is my rectified output. Yes, no, correct? So this dotted line is my rectified output. Don't draw this right now. Now, what I want is, listen carefully. This is here Vi. Actually, we wrote last time Vi by 2, right? But it's okay. We can call this also Vi. This also Vi. And what is Vi? Vm sine omega t. This is in phase, this is out of phase. That's the only difference. Now, please listen over here. Whenever, listen carefully. You have drawn the circuit diagram, now listen carefully. Whenever the diode, see here, whenever we have a diode, then we have a capacitor in the circuit, right? Let us consider the scenario. So we have a C, we have R, they're connected in parallel. It will allow AC to pass through. Now, listen carefully. There is something called as charging time constant called as tau C. And there is something called as discharging time constant called as tau D. Listen, very important concept, don't talk among yourself. This is charging time constant tau C. This is discharging time constant tau D. Yeah, please concentrate there. If you miss out and you won't understand this. Yeah. So when the diode is on, we know that it will replaced by a short circuit, right? That means the current will flow over here and some amount of current will flow over here. Yes or no? Because they are in parallel, the voltage will be in parallel. But the current definitely will split up. So whenever the current flows through the capacitor, it will charge the capacitor. And we have to see what is the charging time for it. Now, what will be the charging time? This coming into picture. Resistor is not coming into picture because it is charging via the capacitor only. Just listen carefully. So, whenever the diode is on, its on-state resistance is very, very small. So, on-state resistances are on for the diode and its value is very small. Maybe around, let's say, 1 ohm to 3 ohms. Very small value. But whenever the diode is on, its on-state is less means what? It allows more current to flow. There is off-state resistance also, on-state resistance also. So, diode is on, its on-state resistance is this. It is multiplied by C. Now, normally, what is the value of C in microfarad? Correct? Okay, and this R on is in 1 ohm or 3 ohm. So let's say the C value is 100 microfarad and R on is how much? 1 ohm to 3 ohm. So tell me what is this RC time constant tau C? Just multiply the 2, right? Let's say R on is 1 ohm. So what will be the RC time constant? 100 microfarad. 100 micro into 1 second, right? So how much is that? 100 microsecond. That is same as around, I think, 0.1 millisecond, right? Whatever the charging time constant. So that means diode takes 0.1 millisecond to charge. बराबर है? Did you understand this much? अभी सुनो, next sequence सुनो. Charging time is associated with on-state diode. Now, in the second case, when the diode is off, let me draw over here. This is when the diode is on. Now, if the diode is off, let me redraw the circuit over here. Listen very carefully, very important concept. So that means if it is, you know, the capacitor voltage charges exponentially, right? So this is my capacitor, this is my diode. Now suddenly this diode was turning on, it has turned off. What it will do? Off matlab it has become open circuited. ऐसे. Now here the diode is off now. So when the diode is off, there was some stored charge on the capacitor. You know, capacitor is an energy storage element, it stores charges. So let's say it has stored charge in this form. Okay, let's say it has stored some energy in the terms of charges over there across the capacitor. Abhi kya hoga beta hai? This diode T1 is off, so it will be replaced with a open circuit. Now tell me, can the capacitor charge via this open circuit? No. Here is my AC mains, of course. So where it will discharge to? It will discharge via this resistor. When it discharges, its voltage across the capacitor starts reducing. Is that clear? You know the charging and discharging curve? Charging, discharging. Are you understanding? So during discharging, now tell me, during discharging, where is my RC 10%? This value of R, correct? And this value of C. Okay? So what is this value of R? Let's say this value of R is 1 kilo ohm. And what is the C value? 100 microfarad. So multiply this 1K into 100 micro. Please do this and tell me how much it is. Is it, tell me the in time, how much it is? 0.1 second. Correct? 0.1 second. Now, why I am stressing on this? Charging time is 0.1 millisecond. This charging time is 0.1 second. Matlab, which is faster, charging or discharging? Which is faster here? Charging, it takes 0.1 millisecond and discharging takes a long time. Now tell me, in an AC signal, if it is an AC signal, listen, I will connect all the three together. Now if I have an AC signal like this, normally AC means is 50 hertz, right? So what is my time period? 1 upon 50, which is 20 millisecond. Is it correct? So that means one cycle is around how much? And what does the full wave rectifier do? Full wave rectifier will rectify the same signal and the frequency same will be ना. So एक cycle को कितना चाहिए? 10 milliseconds. Yes or no? Now listen carefully what happens. Understood? Charging time कितना चाहिए? 0.1 millisecond. This charging time is how much? 0.1 seconds. And how much is this period? 10 milliseconds. So that means this period is how much? 0 to 10 milliseconds. This again 20, this 30. This you have followed. So this is nothing but around. We have taken an example, 10 millisecond. This is 20 millisecond. And this is 30 millisecond. Now, let's see how this circuit will work. Now, please concentrate over here. I'm explaining you the working over here of filter circuit. Now, listen carefully. Initially, we assume the voltage across the capacitor to be 0. Matlab capacitor is not charged. So at time equal to 0, the voltage across the capacitor is 0. Is this correct? Okay. Now what happens? Now what is this value? It reaches a maximum value Vn. Correct? Now your diode D1, I'm not writing anything. I'm just explaining. During the positive half cycle, listen carefully. This is positive and this is negative. This is positive and this is negative, which will make diode D1 on. So D1 becomes on. So where will the current start flowing? To the capacitor. And as soon as the current starts flowing to the capacitor, it starts charging. Now what we said, it's the voltage across the capacitor will be, charging instantaneously. How much time it takes? 0.1 millisecond. और ये कितना है? 10 millisecond. So what happens is, charging matlab, it's same is appearing at the output. Okay, so and this signal is changing at a slower pace. So what will happen is the capacitor. Let me just draw a little thicker line. So what happens in the first half cycle? Capacitor charges instantaneously with the input signal because its time constant is very less. It doesn't have time to react, so it reaches the peak value. Now what will happen? Matlab capacitor is charging up to Vm now. Now what will happen? Maximum has reached. Now it will start to decline. अभी क्या होगा? Capacitor has reached the maximum value. Now what will happen? After that, what should happen? It should fall down, right? It should follow the input. So what will happen after that? As soon as the capacitor voltage, suno abhi dhyan se. Now capacitor voltage is how much internally? Vm, and it's trying to go beyond Vi. बराबर है? So मतलब क्या हो गया? This capacitor voltage is Vm, and this voltage is Vi only. And now this is trying to be greater than this. So what will happen? It will turn off the diode. So T1 becomes reverse bias. समझ में आया what I'm saying? But ये voltage, the cathode voltage is trying to becoming greater than your anode voltage. देखो इधर, अभी ये ऊपर है. Now it will fall down. So temporarily, if it falls down, your Vi is reducing, but Vc is same. So if Vi reduces, that means your diode is reverse bias. Diode off हो गया. Diode reverse bias means diode is off. Suddenly after reaching the peak value. Understanding why? Because now Vi is reducing, but capacitor cannot suddenly discharge, right? It has to maintain that charge. Okay? Capacitor off हो गया. Now when the capacitor is off, what is the discharging rate of the capacitor? 0.1 second. मतलब 0.1 second number is very slow. मतलब what you mean is ऐसे 50 cycle आएंगे, 50 cycles such, then it will discharge. What I mean is this. See, I'll actually show you. So tensor cycle means ये 10 second है. Tensor cycle means it is 0.1 second, right? Okay, so that means the capacitor voltage will completely discharge after 5 cycles. मतलब it's quite rapid. समझ गए? The charge on the capacitor will be over after 0.1 seconds. Will discharge 0.1 seconds. So what will happen? For the first cycle, it will discharge slowly. So now what will happen is capacitor does not have diode is off. So diode is behaving as open circuit. This is the scenario. So capacitor voltage, what will do? It will discharge via resistor with a discharging time constant of 0.1 second. And what will happen after this is all. And ये slope कहाँ से decide होता है? It depends upon the discharging time constant. ये R कितना है, C कितना है? It will be more steeper. It will be almost straight if you select a higher value of R and C. Are you getting it? अभी क्या होगा? Now what will happen? Now it has reached up till here. Again, let me call this point as A. 0 to A, you have understood? Capacitor charging instantaneously, diode is on. After A, what happens? Diode becomes off because anode voltage is lesser than the cathode voltage, and the capacitor starts discharging via resistor RL. Okay, now we have reached point B. What will happen after that? At point B, we are in the negative half cycle. Remember, we are in the negative half cycle of input. So negative half cycle of input matlab D2 is turning on now. Now D2 turns on. Again, the capacitor charges instantaneously. Okay, so capacitor will charge instantaneously towards the peak value. Now what will happen? Same story. The anode voltage of the diode D2 is lesser than the cathode voltage. Again, if Vc is greater than Vi, then diode D2 will be off. After point C, let's say. So after point C, diode D2 becomes off and capacitor again discharges via RL. So the discharging rate will be same now. Okay, and this will continue till D. In D, what will happen again? D1 is turned on and it reaches up to point E. After E, what happens? Again, the diode D1 turns off and the capacitor discharges via RL. And this is how you get the wave. This is how you get this wave. I guess you have got the same waveform during your lab sessions also. Yes or no? So yeah, this is it. Draw the waveforms now. Acha, can you tell me the period until where the diode D1 is on? Up till here. बराबर है ना? तो here D1 is on. और यहाँ पे A to B तक D1 is off. Okay. Then B to C, D2 is on. Okay. And from D to E, D1 is on. Don't worry, whatever I've said is written in wordings. I'll send you the document. Right now, you draw the waveform. If you have a doubt, you can ask. I again repeat till the time you write. So during the positive half cycle of the input, your diode D1 is forward bias. So it charges instantaneously with the input voltage. It charges till the value of Vm. After Vm, the input starts decreasing, but the voltage across the capacitor remains the same. So that's why the diode D1 becomes reverse bias. Now, since the diode is reverse bias, it cannot discharge via the diode. It has to discharge via the resistor. So it will discharge with a discharging time constant of 0.1 second. Okay, and that is the period A to B. At B, diode D2 turns on because it's a negative half cycle, right? So from B to C, diode charges, capacitor charges instantaneously with the input voltage. Okay, again it reaches the maximum value of Vm. After Vm, the Vi decreases. So therefore, diode D2 turns off. So when a diode D2 turns off, it discharges via RL, and that is the phase C to D. Again at D, diode D1 turns on, and again the capacitor charges instantaneously till the maximum value E, and after E, the diode turns off because again it is becoming reverse bias. So that's the story. So this blue color waveform, which I've drawn over here, let me draw this also. So this dashed line is my capacitor filter output. Did you understand the working little bit at least? You read the paragraph, I'll share the document with you all. Now, tell me the ripple. You say na ripple voltage how much? So, if I expand this waveform, what is the amount of ripple which I see over here? This much. Can you see I'm making this line over here like this? Okay. So, basically, from here to here, this is the peak value, right? From here to here is my ripple voltage, VR peak to peak. This is my ripple voltage. This is my AC content in DC waveform. This is the ripple voltage. You remember in your mobile battery charger experiment, you have measured this ripple voltage. It is in few millivolts compared to the waveforms. And normally the ripple voltage should be less. Now, if I want a more better filter, what will I do? Would I increase the value of C, or what will I do? If I want this better, I will require that this B point should come much ahead, closer to Vn. That means my waveform should be like this, right? So I'll have a better, lesser ripple and better filter. So for that, what you will do, either increase C or increase R. R increasing is not advisable, so increase the value of C. That's why in your lab we have taken 1000 microfarad, if I am not mistaken. 1000 microfarad liya in your mobile battery charger, if you remember. Anyways, this is the working of your filter circuit. Now I'll show you the document where this is documented. So no worries, if you have not taken the theory, everything is covered. See here. I will explain systematically what happens, everything. Yeah. This is not required for you all. Current range to the waveform is not required. So this is cancelling it out. Just everything is there. See working. Yeah, that's it. The current waveform you don't have to go to. This is not there for you all. So I'm cancelling it out. Nothing else is there. Okay. This derivation is also not there. So lot of cancellation is good news for you all. So up till point 14 only you have. Okay. The working. You go through the working and explain in your own words. Like I have explained just now over here. Okay. Just the correct circuit diagram, correct waveform, and the correct explanation is required to explain this topic. So filter circuits, it's completed. You have understood? So here we complete module number 4.1. Now let's go to module number 4.2. So write down. Radha, I will use the previous PDF and show it to you. Yeah. So okay, fine. I'll use this PDF. This I have used last time. I'll use it for today. It's fine. Okay. So please concentrate. To understand Zener diode, we have to understand what is avalanche breakdown. Do you know what is avalanche breakdown? You know what is an avalanche? What is an avalanche? There is a slope. At the top of the slope, a lot of snow is there. So maybe a small pebble, a pebble of stone is carried. And as it moves along, it carries momentum, it carries mass also. And by the time it comes down, it becomes an avalanche. So that is what is called an avalanche, right? But initially, it's a momentum and the amount of mass is very less. Okay. By the time it comes down, it becomes an avalanche. So that is what is called an actual avalanche. All right. But now, what does this avalanche breakdown do? You remember PN junction diode? How does the PN junction diode break down? So PN junction diode breakdown due to avalanche breakdown. And there is another breakdown, Zener breakdown. So both the things I'll explain you now. Are you all ready? So write down the heading, avalanche breakdown. Okay. It bracket में लिखो happens in PN junction diode. Happens in PN junction diode. Avalanche breakdown. Now listen carefully. Just listen, no need to write anything. I'll give you this, provide this PDF. So, tell me, if I have an N-type silicon, concentrate over here please. If I have an N-type silicon of length L, okay, and I apply a voltage to it, what is my electric field given by V by voltage, right? Yes or no? So length is L. So if I decrease the length, my electric field will increase. Or if I increase my voltage, my electric field will increase. This you understand, right? So either by increasing the voltage or decreasing the length. Now see what happens. This is my energy band diagram in reverse bias. Now what you do is you have a PN junction like this. Can you see what I'm drawing? Yeah. Reverse bias, how will I draw? Okay. So what happens in reverse bias? What do we have? Forward bias current is like this, right? But reverse bias we have how much? Very small current, right? So in reverse bias we have something called as saturation current, which is almost parallel to the x-axis because it's in nanoampere. All right. But let's say this voltage is 20. Okay. So let's say someone has given you a task to keep on increasing the value of reverse voltage. So this reverse voltage, let's say call it as VR. So currently VR had 20 volt, minus 20 volt basically. So it didn't do anything. Your reverse saturation current was flowing. Now, whoever was operating has gone back. He doesn't understand the meaning of increasing, incrementally. He has increased suddenly from 20 to 50. Still, you don't get any significant current. You get only a constant current over here. Now, that guy has really gone mad and he has increased beyond 100. Now what has happened? The moment it increased beyond 100, your diode has burst, and he couldn't find a reason why. This is a irreversible phenomenon. If a diode enters a avalanche breakdown, it will never recover back. It's a waste. Okay. So after that 100 volt, your current will increase very fast, and within no time it will burn out. Your current will increase too high, it exceeds the limit rating of the diode, and the diode will be off because temperature has reached very high. So यहाँ पे क्या हुआ? The reason for this sharp increase in the current and hence damaging the diode permanently is called as due to avalanche breakdown. Okay, and for practical diode, this voltage is around 75 to 100 volts. So once your breakdown voltage is reached for the diode, current starts flowing very rapidly in the reverse direction. Current reverse direction में नहीं flow होना चाहिए, but अभी flow हो जाएगा, and it will, the diode will be damaged due to avalanche breakdown. Yeah, students, please keep quiet there. Okay. Now tell me, what do you see in this energy band diagram? You see P side on the left hand side, and you see N side over here. And this height is BBI is the internal barrier created due to balancing process, and VR is my reverse voltage. Now, if I increase this barrier even further, what will happen? The height will keep on increasing, okay? But yeah, this will keep on increasing, right? Now, these electrons which are there on the P side, they are minority carriers. Now, what I told you, this W also will keep on increasing, right? Why W increases as the reverse voltage increases? Because more and more carriers will be pulled out of the carriers, right? So, ऐसे होगा देखो. You operate reverse bias. So, initially, my depletion region was this much, right? But now, due to increase in the voltage, the depletion region will be like this. Are you understanding? So, this becomes my depletion layer. So, no current should flow, right? But now rapid current flows. So, let's see how it happens. Now, see here. So, that means, do you agree that if I increase the voltage VR, my width of the depletion layer increases? Yes or no? Are width of the depletion layer increases, no? Because more and more carriers are moving away from the junction. So, this becomes my depletion layer now. Now, what happens? See, if I increase the voltage, I have a very large electric field in this direction. My electric field is in this direction, right? That electric field is going from right to left, and electrons will run away from the electric field. So electric field is becoming even more powerful, more and more powerful. So what it will do is, these electrons, minority carrier electrons which are there on the P side, they get accelerated by this very high electric field. Okay, and when something has reached acceleration, let's say even a cycle, when it moves at, what happens? This back. What? Now, yeah. So what I'm saying is the momentum is very, very important. So what is the momentum over here? Yeah. The momentum is, even if a bicycle travels at the speed of 200 or 300, the impact it creates is very high. Even if a train is traveling at 5 or 10 kilometers, the impact it creates is lesser. Or if the train is traveling at a speed of 100, 200, anyone comes in between will be gone. If a bicycle is traveling at a speed of 10 or 20, anyone is coming will not be affected. Even a bicycle person will fall down. But if a train with a lot of momentum, even traveling at 20 can damage the person or anyone there. Okay? What I mean is, these accelerated electrons are very less and they are moving in the semiconductor medium. So when it achieves a very high energy, what it will do? It may hit other particles and it will create electron hole pairs. So one electron will create another electron hole pair. That becomes accelerated. They will create another electron hole pair. This way, starting with there are, let's say, 2 electrons, and at the end it leads to 2 like electrons. So now many electrons from p side are traveling to the n side. So n side conducts, start conducting electricity. Similarly, holes from here gets accelerated from the electric field. You know what is kinetic energy? What is potential energy? Kinetic energy. So these electrons gain kinetic energy from the electric field, and they start traveling at a tremendous speed out. Run away from the electric field like this. Electrons are moving from left to right. So what it will do? It will hit other atoms and it will create electron hole pairs. And in this way, in no time, lot of electron hole pairs are created, and that will lead to avalanche breakdown. Understood? No. See, this is the crystal structure. Inside crystal structure is like this only, na? We have a phosphor atom. Can you see that? Phosphor atom P and surrounded by 4 silicon atoms. So this accelerated electron can hit this silicon atom. It can disperse this electron. Now this electron becomes free electron, right? So we have 2 electrons now. One accelerated electron and one that dispersed electron. Correct? So now 1 became 2. Similarly, this will go on happening. This accelerated electron will create electron hole pair, and that will lead to very heavy conduction of current in reverse direction. Okay, so that is what happens over here in avalanche breakdown. So accelerated electron collide with silicon atom, knocks off its bond electron with enough kinetic energy. Now we have 2 free electrons. These again gain kinetic energy from the electric field and knock silicon atoms, which gives rise to more free electrons. Okay, so due to this collision, the number of free concentration carrier increases rapidly. Then there is a sudden jump in the reverse current. So this breakdown causes what is called as impact ionization. Have you heard of this term before? What is impact ionization means? High energy charge carriers can knock out bond electron from silicon. See, silicon का bond electron knock out करने के लिए कितना energy चाहिए? Energy band gap जितना 1.1 electron volt. So if an accelerated carrier is breaking that, that means it's a big deal. So that process, that high energy charge carrier can knocking off the bond electron from the silicon atom is called as impact ionization. Okay, you have to use this word impact ionization when you explain this process of avalanche breakdown. Okay, so this is called as avalanche breakdown effect. It happens at a much higher breakdown voltage. See, this does not happen at 10 volt, 20 volt, 50 volt. It happens at 100 volts. So during that case, the accelerated electron starts affecting the entire system, and they lead to a very heavy current flow. This sharp increase in reverse current is due to impact ionization. Is that fine? So this is how a PN junction diode breaks down, and it's an irreversible process, but it cannot be back to the normal condition. Write down the topic Zener diode. Zener diode I'll tell you the reason exactly how Zener diode and PN junction diode are different. So Zener diode is, listen carefully, Zener diode is same as PN junction diode except one difference. What it is? It's very heavily doped. Meaning what? NAND. Do you know what is NAND? Acceptor carrier concentration in P type and donor carrier concentration in N type. It's way higher compared to normal PN junction diode. Okay. So this is the symbol of a Zener diode. Please draw it. Zener diode symbol. Can you see the difference between the Zener diode symbol and a PN junction? It has these arrows both the direction. Matlab kya? The current can flow in both the direction in a Zener diode. So Zener diode in forward characteristics behaves exactly the same as PN junction diode. There is no difference. Maybe when it starts conducting the barriers, the VBI which is being created due to the balancing of drift and diffusion phenomena, that VBI voltage will be lesser. Why? Because there are more number of carriers available now at P and N side. Okay, so depletion region width will be smaller comparatively. Okay, so Zener diode is very heavily doped. PN junction is slightly doped basically. Okay, Whereas Zener diode is determined, structure is determined like this. You don't write Pn, you write P plus and N plus. Plus indicates higher number of concentration carriers. What is the meaning of concentration carrier? Matlab, in the entire silicon crystal lattice, there are silicon atoms bonded by other silicon atoms. So those silicon atoms are replaced by impurities, that is phosphorus, group 5 elements. So more number of phosphor atoms are present in case of Zener diode, and more number of boron are present in case of N side. Okay. So basically, it has a controlled reverse characteristics. Controlled reverse characteristics, you will understand. And the reverse current is reversible. Meaning, in PN junction, if you reach the reverse voltage, it was irreversible. Here you can, the current can flow in the reverse direction in controlled manner. Meaning, even at 2 or 3 volt also, or 10 volt also, the reverse current flows in milliamperes. Whereas this was not possible in PN junction diode. Now let's see how this happens. And one of the applications of a Zener diode is Zener as a voltage regulator. See, this is what happens. So now, I told you in forward bias it's exactly same as your PN junction. What is the difference? That VPI barrier, which you see over here, W is slightly small in case of a Zener diode compared to PN junction diode. So tell me, what is this? Describe. Tell me, what do you see over here? More number of carriers on the either side of the junction. So what happens in forward bias? See, electric field ka, what is the formula? V by L, right? If L is small, electric field will be more. So into forward bias, the electric field is more. Okay. So what it does is it the current rapidly flows to the exponential manner, much faster than your counterpart PN junction diode. So that's the only difference. This, if I compare, if this is my forward characteristics of PN junction diode, my Zener diode forward characteristics will be this. It will reach a higher current value much at earlier voltage because of a heavily doped N and P side. That's the only difference. Well, PN junction in forward bias you all already have understood, right? What happens in PN junction in forward bias? Carriers flow across the junction due to diffusion phenomena. Now, the question is, what happens in reverse bias? As I told you, the W is very, very small. Yes or no? The W, the depletion region width is very small in case of Zener diode. Let's say it's 10 units in case of PN junction, it's 1 unit in case of Zener diode. So very, very small. Okay, let me show it to you in terms of diagram. So if I have a Zener diode, if I have a PN junction diode like this, its depletion width is this. For a Zener diode, the depletion region will be very small in this much. And why it happens? Because it's heavily doped. Okay. Now reverse bias mein what happens is I have to explain you in terms of energy band diagram. This is related to something called as quantum tunneling. Have you heard the word quantum? Quantum tunneling. Now it's like it's a difficult concept to explain, but have you heard of there is a scientist now named as experiment was there, a cat, whether it's alive or dead, 50% chance. So same way, this is scenario. Now listen hypothetically, everyone understand, please. Please understand this, everyone. Concentrate over here. Now, this is my energy band diagram in reverse bias. This you all agree, right? This is how it looks like. Now, there are electrons in the valence band. Okay, electrons are there in the valence band. Now, instead of these electrons gaining energy, reaching over here and then coming down, what happens is because the W, the barrier, is very, very thin, something else happened is this. These electrons tunnel away from P region into N region directly. And that process is called as electron tunneling. So where do they get energy from? They get the energy from the electric field itself. Now, pehle kya ho raha tha? These electrons which are over here, they were very few. They were traveling like this, right? And they were very few. That will lead to an avalanche process. But why this is a controlled phenomena? Because यहाँ पे avalanche नहीं हो रहा है. यहाँ पे the energy is spent in breaking that bond. And so what is happening is electrons are traveling through the depletion layer and then reaching the other side. So by the time it will hit the immobile carriers in between, so it will lose its momentum. Yes or no? Are you understanding what I'm trying to say? If let's say if a person is there and he's thrown off of a very high clip, what will happen? That person will eventually die. Eventually, that is that person constantly accelerating towards the earth, or it achieves a constant velocity? It achieves a constant velocity, and by the time with that force it hits the ground, instantly within 1 second the person is dead because all the bones are broken. What will happen now? You must have seen a lot of stunts carried out in movies where the superhero or supervillain jumps into the water, right? It is valid up till few meters, but once you are 1 kilometer, 2 kilometer, or 10 kilometers, above the sea level, and if you try to attempt it, your water will not appear as a water; it will appear as a cement, and instantly when you go down, gone, you're dead. Why? Because you're accelerating by the g. G is 9.8, right? So you're accelerating towards this thing, and the entire all the bones in the body will break instantaneously, and that is what will happen. All right. So this electron tunneling, the energy which is gaining from the electric field is spending in breaking the barrier. But the हो क्या रहा है पता है? See here. This is my Zener diagram. This barrier is very very thin. Let me expand this part so that you understand it what happens. Here I go. Please listen to this. So this is my Zener diagram. It is P plus N plus, and now my barrier over here is very small. So now what happens is the carriers which wants to go on to the other side directly go on to the other side and tunneling through the barrier. That's it. They directly go without any hesitation and reverse bias. And this was only possible in forward bias, no? That the carriers diffusing across the junction, but this is happening over here due to quantum tunneling. Just as if that you have a gun and you are hitting the wall and the bullet is coming from the other side of the wall. If the wall is very thin, hypothetically not true, but this is true for the accelerated electrons over here. Okay, it's easier to go through the barrier. Then, what is the other way the carriers can go? It will gain energy. It will gain energy, move up, and then go down with accelerated carriers. That is avalanche breakdown. But instead of going up, what it does is it tunnels through the barrier because it's very, very light. The barrier is very, very thin. So this is called as electron tunneling or quantum tunneling. Okay, but that's the only explanation of why it is controlled. Because these carriers, when they release to the other side, they are not contributing to unimaginable high current in milliamperes current. The current is very small. That many number of carriers, that many amount of current traveling. So this is called as Zener breakdown. Okay, the current increases in the reverse direction, but in a controlled manner. Okay, understood this? I don't know. I have written over here certain things, so you can read about it. It's about what I told you. Now, one more advantage is there. This Vz is the breakdown voltage. It is called as a Zener voltage. Can you see what advantage do you see over here? The current increases in a controlled manner. That is true. This is in milliamperes. What else do you see? You see that the voltage is hardly increasing, but the current is increasing a lot. So let's say this is 6 volt, and this value over here is 6.1 volt. So between 6 to 6.1, hardly there is change in voltage, whereas current is increasing. So where it is applicable in voltage regulator, we want voltage not to change, current can change. So that's why the application of Zener diode is Zener as a voltage regulator. So hardly increase change in the voltage, but you get a controlled testing. So that's why Zener diode, can you see the symbol over here? So diode, this indicates current is flowing in both the directions, forward bias and reverse bias. Also, what is the forward voltage? Forward voltage of a Zener diode? It's very maybe around 0.6 to 0.5, and reverse voltage is it's in the designer's hand. If you want breakdown voltage to be 2 volt, there are Zener diode available with 2.2 also. If you want 10 volt, they are available in 10 also, 15 volt also available. Meaning this VZ is under designer's control. So we can select the amount of doping and we can make the Zener diode work for that particular breakdown. But we are controlling the diode when to break down, when not to break down. अगर मुझे 5 volt constant चाहिए reverse bias में, I want to, we have used the regulator, right? Regulator IC. We can connect the Zener diode also over there, and that will lead to a constant value of breakdown Zener voltage. Okay, that's a Zener voltage only. Understanding this? All this I've written over here in words. You can go through it. This is my Zener effect. So please draw this diagram. This is the reverse characteristics of a Zener diode in reverse bias. Reverse characteristics of a Zener diode in reverse bias. And the zone which I marked over here is the Zener effect. Do you see IZ minimum and IZ maximum? So it's always prescribed that when you use a Zener diode, you should be within this limit rating. You should not exceed the limit rating. Where you will get this information from IZ minimum, IZ max, VZ from the data sheet of the Zener diode. And do you see one more thing over here, that the Zener voltage is constant in the reverse bias, right? Almost constant. Okay? Completed or no? Yes? Okay. This is a difference between avalanche and Zener breakdown. If they ask you in the exam, you can write few different points. And also one more point is there, avalanche breakdown occur in PN junction diode and Zener diode occur in Zener diode. Now write down, next, Zener diode as voltage regulator. Last topic for today. Zener as voltage regulator. Now draw the circuit diagram over here. RL. This is the diode, Zener diode. This is RS. This is VS. This is Zener diode. In the exam, if you draw a diode instead of a Zener diode symbol, it will be wrong. So please draw Zener diode only over here. This is the load current IL. This is IS. And this is IZ. What is voltage across the Zener diode? VZ. Reverse voltage, right? So what is IL called as? Load current. VZ is Zener voltage. IZ is Zener current. And IS 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 source current. Okay, drawn the circuit. Now, what is the aim? First of all, let us write the aim. How it acts as a voltage regulator. What do you mean by voltage regulator? It will keep the output voltage constant irrespective of the changes in the line voltage, line current, or in the changes in the load current. Okay. So write down aim is to keep VL or Vout constant irrespective of line and load variation. Okay. The aim of a Zener regulator is to keep output voltage or load voltage constant irrespective of the line or load variations. Now I'll explain what you mean by that. Now, tell me, where do you get this Vs from? This Vs is obtained from here. You remember this diagram? This is the diagram of AC DC power supply, right? You get a DC voltage, right? This DC voltage is same as this DC voltage, Vs. So where do you get it from? You get it from AC mains. And AC voltage mains can change from 230 to 250 volts, right? So it can fluctuate. Yes or no? So there can be a change in the Vs. So Vs can change due to change in line variation. So these are called as line variations. Vs value can change due to line variation. Okay. So this is number one point. Vs can change. Vs changes due to line variations. Okay. Now tell me, do you know your KCL at this point? So tell me what is KCL at this A point? IS is the incoming current and IZ and IL are outgoing current. Yes? Okay. Now tell me what is the voltage R, how do we calculate current? This resistance RS. How do you calculate it? Simple. See, you have a resistor. On one side you have Vs, other side you have Vz, and this is RS. This is IS. Tell me how do you calculate the RS now? Vs minus Vz upon IS, right? Yes or no? Now what is IS? Oh, so IS is IZ plus IL. Yeah. If I calculate the value of IZ here plus IL, how much is that? V Vs minus Vz. Vs should be greater than Vz. KCL by KCL will be Vs minus Vz only. You are assuming Vz is greater than Vs. No, it will be this way only. See, voltage at node A is same as Vz. So Va is same as Vz. Now if you apply that thing, you will get the same thing only. Okay? So Iz plus IL is Vs minus Vz upon Rs. So tell me what is Iz? Vs minus Vz upon Rs minus IL. Correct now? Yes or no? So that means IL is depending upon, and what is load current given by? Load current is given by, see this Vz voltage, VL voltage and Vout voltage are all same. Parallel में connected है ना? So load current is what? Vz or VL upon RL. Do you agree to this? Only with the help of these two equations we can explain the entire Zener as a voltage regulator circuit. Okay. Now, for proper operation of this Zener diode on होना चाहिए, right? In reverse bias. So for that, what you would require is ये Vs voltage मेरा should be greater than Vz. Why? Then only it will be in reverse bias, ना? And अगर ये 10 volt है, so this will be 7 volt. Why? Because some voltage is dropped across the resistor also Rs. Yes or no? So basically the general norm is Vs voltage should be 2 to 3 volts higher than the Zener voltage. So for proper operation of Zener, number one condition is Vs voltage should be greater than Zener voltage. Alright. Now, what are the variables in this equation? So whenever Vs is greater than Vz, then the Zener diode operates in the Zener breakdown region. Okay? So tell me what are the variables over here which change, which can change. IL can change, Vs can change. What are the constants? What are the constants over here? Load current can change, no? Vs can change. What are the constants? Vz and Rs. Yes or no? Why? Because Zener voltage so change nahi hoga. Rs also is a resistor, it will not change. So what are the changing parameters over here? IL and Vs. And constant are this. So now we'll start with so these variations in IL variations will be observed. Just wait. IL variations will be observed if you change the value of RL. And these variations are called as load variations. Okay? And these variations are called as line variations. Okay? So now we'll study if my load changes, how will my output will be constant? If my line changes, how my output will be constant? But output constant ही होना चाहिए ना, irrespective of IL changes, VH changes, my regulator output should be constant, should be equal to my Zener voltage. Yes or no? Okay. So first, we'll study source or line variation. So please understand. Listen carefully now. I'll be using this one diagram to explain you both. Listen very, very carefully. Everyone pay attention, please, for last few minutes. Now, if Vs changes, now line variation means what? If Vs changes, okay, and RL is constant. मतलब दोनों variation एक साथ नहीं कर सकते ना. You study one, you change one, another one you keep constant. So first case में we are studying line variation. मतलब Vs is changing and RL is constant. मतलब load current is constant. ठीक है? So Vs is changing. Let's say it's increasing. अगर मेरा Vs is increasing, what will happen to Is? Vs increasing to Is will do what? अरे देखो ना इनका equation. Vs increasing, so what will happen to Is? What will happen to Is? Is will also increase, no? So Vs increases, the source current increases. If the source current increases, what is source current given by? Iz plus IL. IL is constant. So what should happen to Iz? See, Iz plus IL, right? Okay. So इसमें से IL is so constant. So what should increase? Iz increases. So if the load current varies, if Iz varies, will my Vz remain constant? Can you see this diagram? What is this reverse characteristics? इसमें क्या बोल रहा है कि Iz is varying, Iz is increasing. Is my Vz constant? Yes. So even if Iz is increasing, my Vz remains constant. provided I am under this limit. I am not exceeding this 100 milliampere. समझ में आया what I am saying? Yeah. So over here, if my line voltage is increasing, my Vs is changing, Is is increasing, my Iz is increasing, okay, and due to that, even if my Zener current increases, my Zener voltage will remain constant. So my output will be constant. Output voltage will be constant. Similarly, in the exam, you can explain similarly if the load Vs decreases, Is decreases, Iz decreases, even if current decreases, your current voltage will be constant, provided it doesn't fall below Iz minimum. Okay. Now, let's test the other case now. Now, what is the other case? Load variation. मतलब RL change हो गया. RL changes. But what is constant? Vs is constant. Okay. Now tell me, if load increases, IL increases, RL increases, what will happen to IL? Come on. RL का value मैंने बढ़ा दिया. See, VL is I into RL, which is constant, right? Agar if I am increasing the value of resistance, so IL will reduce. Simply, so IL will reduce. What it will do now? What is IS given by? So IL is कौन हो रहा है? IS constant होना चाहिए ना? IS because VZ is constant. See, IS is VZ upon RL, right? RL अभी क्या हो रहा है? IS, where is IS over here? Here. IS is VS minus VZ upon RS. अभी हम लोग क्या assume कर रहे हैं? VS is constant, VZ is constant. So can you say IS will be constant? Yes. So here in this equation, if RL increases, if load changes, load current is decreasing. If this is decreasing, IS is equal to IZ plus IL. So what should happen to IZ? This will remain constant. So what should happen to Iz? To maintain this constant, Iz should increase now. And even if Iz increases, your Vz will remain constant as we have seen already. So in other case, if RL is reducing, IL will increase and dependently your Iz should decrease. Even do we do that, your load will remain constant. So that's how you explain. This is how your Zener diode works as a voltage regulator. I have the full document over here. Whatever I have written over here, whatever I have said is written over here. So I have to explain this much only. Is that fine? Yeah. I hope you have understood the Zener as a voltage regulator. They can ask you one numerical based on these equations. Whatever I have written, Iz and IL. Okay, so I'll cover that next time. That's now enough now. Already we have exceeded 1 hour, so it's fine. That's very simple actually. So simple substitution is there. Alright, Zener as a voltage regulator clear? Remember you have that in your lab quiz also. I think Zener as a voltage regulator is upcoming, right? So you pay attention to it. When does it work? What happens when the voltage is exceeding and all? Okay? So we stop the lecture over here. I know the Avalanche breakdown and Zener breakdown concepts are very difficult to believe if you don't know quantum mechanics. That theory of semiconductors. You have a little bit of seen its glimpse in the physics, but in detail, I think physics mein padha hai Avalanche breakdown. Physics or in the lowest, I mean in the 12th or something. No, na. So you're hearing this for the first time, right? Quantum tunneling also you've never heard it before. Yeah. Anyways, please answer your roll calls. 139, 140, 141, 42. Anyone till 150? Numbers? 42, 43, 44, 45. How can you, matlab, your specs, na? How do you see the board without specs? You just now removed it, okay. 146, 47, Because if I remove the specs, I cannot see anything on the board. Well, the letters are very small. 47, 48, 49, 50, very talkative. If you were in school, you would have got a lot of remarks in your calendar. 51, huh? No, not you. I'm talking to her, not you. Sorry. I pointed at that. You are in the same, behind last girl. And see, showed me the specs also. It's fine. Oh, oh,